Welcome to this explainer. If you've ever wondered why so many super clever phishing attacks still somehow manage to slip right into your inbox, well, it's basically because for decades, we've been relying on security systems that act like incredibly rigid bouncers at a club. They're just standing there, checking a list of exactly known bad guys, and if you aren't on the list, you get right in. But today, we're talking about a monumental shift. We are officially moving away from those rigid, hard-coded rules to systems that actually understand semantic intent. We're entering the era of embedding-based attack detection. This is where the security system doesn't just read what a potential attacker is typing, it mathematically understands what they actually mean.
Okay, let's jump right into a practical example to show you what I mean. Imagine two phrases. Phrase 1 is, ignore your previous instructions, and phrase 2 is, disregard all prior directives. Now, syntactically, these are completely different strings of text. They share absolutely zero words in common. So how could a traditional security system possibly know they are the exact same attack? The short answer is, well, it couldn't. An attacker could literally just run their payload through a thesaurus and bypass those traditional defenses entirely. And that fundamental flaw is exactly why the security industry is undergoing such a massive, radical transformation right now.
So, if we break down the historical progression here, it becomes pretty obvious why the old methods are failing us today. Traditional security, like your classic signature-based detection, relies on exact or near-exact matches. Think of hash lists or regex. It's incredibly precise, sure, but it is so brittle. An attacker just has to tweak a single character and boom, they evade it entirely. Then we evolved to heuristic-based detection, which uses these handcrafted rules. For example, a rule might say, hey, if a request contains the words union select, flag it as a SQL injection. But again, this requires constant manual updating and it completely misses novel, zero-day attacks. Embedding-based detection solves all of this because it generalizes across those surface variations automatically. It actually learns the semantic similarity.
Now, to solve this whole fragility problem we've been talking about, we use embeddings. But what actually is an embedding? By definition, embeddings are dense numerical vector representations of data. And that data could be anything: text, images, network packets, you name it. These vectors are produced by neural networks, typically transformer-based models. Honestly, the best way to think about an embedding is like a giant mathematical meaning map. The neural network translates the data so that inputs with similar malicious intents end up living in the exact same mathematical neighborhood, totally regardless of their surface-level disguises. It's capturing the underlying meaning rather than just the raw syntax.
But how big is this mathematical map? When we say high-dimensional vector space, we definitely aren't talking about that simple 3D graph you learned about in high school geometry. No way. An input, like a phishing email or a sneaky user prompt, is converted into a vector with hundreds, or very commonly, 1,536 dimensions. That incredible depth is exactly what allows the model to capture the deeply nuanced, true intent of the data. It plots the sentiment, the structure, the context, and the ultimate goal into a single coordinate on a massive 1,536-dimensional grid. It's wild to think about.
Let's trace the actual journey of a malicious input traveling through this pipeline in the real world. A typical embedding-based defense operates in 4 really distinct stages. First up, during input ingestion, the raw data arrives. Maybe it's a sneaky prompt trying to trick a large language model, or maybe a suspicious DNS query. The system extracts the relevant text. Next is embedding generation, where that input is passed through our model to produce that fixed-length vector we just talked about. Then we hit the absolute critical stage, comparison and classification, where the math actually happens. And finally, the system makes a split-second decision. Based on that comparison, do we allow it, block it, quarantine it, or alert a human analyst?
Let's actually zoom in on stage 3 for a second. How does the computer actually know 2 different sentences mean the exact same thing during this comparison stage? Well, we can use distance thresholding, which means calculating the cosine similarity between the new input and known attacks. If the math says they're too close together, flagged. We could also use trained classifiers, anomaly detection to spot weird outliers, or even unsupervised clustering. Alternatively, we can use retrieval-augmented detection. This is where we leverage powerful vector databases like Pinecone or Face to instantly pull the nearest neighbors of a new input and check if they happen to belong to a known malicious neighborhood.
Section 1. Real-world battlegrounds, defending the LLM frontier.
We've talked a lot about the theory, but where is this actually being applied today? Well, we're seeing this intent matching approach used directly against the highest profile threat right now, LLM prompt injections. Adversaries are constantly trying to inject instructions to override system prompts. But beyond LLMs, this tech acts as a total superpower across multiple domains. In network intrusion, it catches zero-day attacks by looking at behavioral features like timing and packet sizes, which, by the way, works even if the payload is completely encrypted. It spots rephrased phishing lures. It groups obfuscated malware families based on API call sequences. It even spots code vulnerabilities and complex fraud patterns that traditional keyword filters completely miss. It's just incredibly versatile. So you might be wondering, how does this stack up against other machine learning defenses? While traditional ML requires a ton of manual feature engineering, though, to be fair, it is quite interpretable. On the other extreme, using a full LLM as a judge provides incredibly deep reasoning about context, but that comes at a massive, massive cost in both compute power and latency. Embedding-based approaches, they sit right there perfectly in the sweet spot. They offer an incredible balance, generalizing automatically using transfer learning while being vastly faster and cheaper per query than asking a giant LLM to evaluate every single input.
Now, because of these inherent trade-offs in speed and cost, embedding detection is rarely ever used entirely on its own. Out in the wild, in production, it works best as the middle layer of a hybrid defense stack. Layer 1 is your lightning-fast rejects and keyword filter. It super cheaply knocks out the obvious, known attacks. Layer 2 is our embedding similarity check, catching all those rephrased and obfuscated variants with very moderate latency. And finally, Layer 3 is your LLM-based analysis. That's your expensive, deep reasoning tool reserved exclusively for the most ambiguous, complex edge cases that somehow manage to slip through Layer 2. It forms a highly efficient, beautiful funnel.
Section 2. Blind spots and limitations, the adversarial complication.
Look, we have to be real here. Cybersecurity is basically a never-ending cat-and-mouse game, and this semantic approach is definitely not a silver bullet. If attackers know you're using an embedding model, they will absolutely try to actively manipulate their inputs. As the research points out, they do this by purposefully adding irrelevant, totally benign text to shift the embedding centroid away. Why? Because injecting all those good words mathematically drags the average point, the centroid, of their vector away from the known attack clusters and safely into the benign region of the vector space. They are literally hiding their poison pill inside a giant mathematical marshmallow.
And this evasion tactic creates a massive headache and a constant, high-stakes balancing act for security teams. On one hand, you have false positives. If you set your similarity threshold way too broad, you end up flagging totally innocent behavior. Like, imagine a legitimate security researcher simply having a discussion about prompt injection techniques. The system sees the semantics of the topic and just panics. On the other side, you have false negatives, where a clever attacker uses semantic paraphrasing or benign text injection to achieve their malicious goal, while mathematically avoiding your known attack clusters entirely. Beyond just fighting the attackers themselves, defenders face some serious everyday operational friction. For one, generating embeddings adds a latency tax to every single request, which is incredibly tough for real-time apps. Then there's the lack of interpretability. Just imagine trying to explain to your manager why a critical request was blocked, and your only answer is, well, it had a 0.12 cosine distance to a known threat. Yeah, that's not exactly actionable feedback. There are also cold start problems, where new deployments have absolutely no baseline of normal behavior, and the persistent threat of distribution drift, where the nature of normal network traffic slowly evolves over time, making your older embeddings completely obsolete.
Section 3. The future of defense, next-generation semantic security.
But hey, the landscape of AI security isn't standing still, and researchers are rapidly patching these blind spots. We are already seeing some incredibly exciting emerging innovations on this front. As attacks start to span across text, images, and even voice, we're seeing the development of multimodal embedding models to stop them simultaneously. There's also a huge push for federated embedding sharing. This is brilliant, by the way. It allows multiple organizations to share the malicious vectors of new attacks they discover to build a collective defense without ever having to share the private, raw, underlying data. We're also seeing self-supervised systems that dynamically learn what normal looks like so they can discover brand new attack clusters completely automatically.
This whole technology represents a monumental shift for the cybersecurity industry. It moves us fundamentally from rigid syntax right into the heart of meaning. It offers incredible generalization that legacy systems just simply cannot match. But as we've seen, it's a wildly dynamic battlefield. It leaves us with one incredibly critical question to ponder as we wrap up this explainer today. As AI continues to write both the sophisticated new attacks and the semantic defenses, who will ultimately win this evolving arms race? Thank you so much for joining me, and as always, keep questioning the data.